Hi guys, welcome back to functional analysis. So today and also in the next video we will discuss one of the big ones in this module, the Hahn-Banach theorem. Some people would go as far as to say that this theorem is the most important one in a first class in functional analysis, and I've seen lecturers probably not at Bristol, but elsewhere, who begin their module on functional analysis by this theorem on day one. Okay, and there is a point to that, because I mean the module is called functional analysis, and so far, unless we are in a Hilbert space, we don't really know if functionals actually exist, right? I mean, besides of the zero functional, but if you are an arbitrary say Banach space, proving that there exists a lot of functionals, it's not so trivial, and this will be at the end of the day a consequence, one of the many consequences of the Hahn-Banach theorem. Okay, and that's why it's important. That's why we will spend the whole section 3.2 in our notes on this theorem and the discussion of its proof as well as its multiple consequences. Okay. Unfortunately, the Hahn-Banach theorem itself is a statement whose proof is not constructive, very much like the proof of the existence of orthonormal basis in arbitrary Hilbert spaces. Also, that theorem will rely on Zorn's lemma in its proof. Okay, so that's why it's, again, one of the non-constructive ones. Okay, but one step at a time. So first we need to prepare some notion here, might be known from user analysis. So if you have a vector space X and S a convex subset, so remember, convexity of a set means that if you have 2 points X and Y in the set, then geometrically the straight line between those 2 points is also in the set. So just this convex, so-called convex combination, theta X plus 1 minus theta Y, is in S for any theta ranging from 0 to 1. That's what it means for a set to be convex. Intervals on the real line are typical examples of convex subsets. And I think I also drew some in 2 dimensions, circles versus stars, right? Okay, so having a convex set, now what's a convex function? Well, this is what's written here. So a function from a vector space to the real line is called convex if and only if, well, you take the convex combination here on the left, you act with f on it, and then it is bounded from above by, well, the convex combination of the images, right? So now the thetas are out here, and you have here f acting on x and f acting on y. On the real line, well, this is actually something one usually knows. So graphs of convex functions on the real line here, those are those whose tangent lines always lie below the graph of a function, right? So sometimes they're called concave up, but he will say those are convex functions. All right, good. So now here's the big theorem. So there will be 2 versions of this. There will be one Hahn-Banach theorem formulated in real vector spaces. That's the first one here. That's why real Hahn-Banach theorem. Will take quite some time to prove it. And then once we understand the real one, then we will formulate the Hahn-Banach for complex vector spaces. That is to say, real vector spaces are vector spaces where the underlying scalar field is the field of real numbers, and complex vector spaces, those are those vector spaces where the scalar field, the underlying scalar field, is the field of complex numbers. All right, so here we go. Here's the statement. So if X up front is a real vector space and P is a convex function, so that's what we just defined up there, then you take a subspace Y and a linear functional on that subspace, small f, and that linear functional is dominated by this convex function. So f of y, which is a real number, is at most p of y, which is also a real number. Okay, so that inequality makes sense because both objects there map into the real number field, and the real number field is ordered, right? So now this is the assumption, and now what it says is, well, you can continue, you can extend. So Hahn-Banach is an extension theorem. You can extend this small f to a capital F, which lives on the whole vector space X. Remember, small f just is defined on the subspace. And you can continue it in such a way that the properties are preserved. Precisely, also capital F is dominated by P. Remember, P is defined on all of X, whereas small f only on Y. All right, so F is dominated on all of capital X by P, and once you restrict yourself again back to the subspace, it reproduces the small f. So capital F really is an extension or a continuation of small f to the whole vector space X in such a way that the inequality is preserved. Okay, that is Hahn-Banach. Notice, by the way, here, in the formulation of this theorem, we do not assume that we are working in a normed linear space. There's no mentioning here whatsoever of a norm. We don't require any closedness, so Y is just a subspace, doesn't have to be closed, right? And that. So these two criteria, norms, the absence of norms and the absence of closeness, indicates that this proof will not rely on all the techniques that we have studied so far, right? So it will be again abstract and it will invoke Zorn's lemma. Okay, it is a continuation theorem and extension theorem. We had in the last video towards the end, we had the BLT theorem that kind of, did a similar thing. Bounded linear transformation that is defined on a dense subspace, then you can extend it uniquely to a whole thing such that properties are preserved. Now here, this is dealing here with linear functionals, and also I should mention that the continuation here that is guaranteed to exist by the Hahn-Banach theorem is in general not unique. Okay, that's a difference to the BLT theorem. Okay, so that's the statement, and now we will prove it. So overall, the idea will be you start with the subspace Y, and then what you will have to do is you have to sort of enlarge Y, say by one vector at a time, hoping that the property of the extension is preserved, and then sort of going one vector at a time. But for this, of course, if your space is not finite dimensional, you can't hope that an ordinary induction would do the trick for you, right? If you were in a separable space, then this would work because you have countable dense subsets. But here we don't assume any of this, so necessarily we will have to play around with Zorn's lemma sooner rather than later. Okay. Anyways, now enough talk. So the proof is split into several pieces. The first one here being this first proposition. This will derive some inequality. So for vector spaces, real vector spaces X, subspace Y, the small f, the linear functional on Y, and the convex function P on X, as in the above theorem, we have the following inequality. For every y1, y2 in Y, and any X which is not in Y, so implicitly writing such a statement implicitly means, we assume that such an X exists. So I don't want to deal with the situation that Y is equal to X, right? I don't want this. So Y is a proper subspace, in other words. Okay, so then pick an element X in this complement of Y, and then two positive numbers, and then, there is some inequality which holds true, okay? And you will soon understand why we want to have this inequality. For now, let's just accept it and just prove it, and then apply it in the subsequent steps of the proof of Hahn-Banach theorem. Okay, so to prove it, it's not hard. So first, set theta, the ratio. So alpha and beta were positive numbers. So let's create this number here, beta over alpha plus beta. This is a positive number for sure, because you take a ratio of two positive quantities, beta and alpha plus beta. And this is also a quantity which is strictly less than 1, right? Because you could find an upper bound which is beta plus alpha which is 1, because you add here a strictly positive number. So definitely this is a parameter in 0, 1. All right, then for any y1, y2 in Y, so let's look at f of 1 minus theta y1 plus theta y2. So f, by assumption, is not a convex function, but it is dominated by a convex function, which is your p. So you have p 1 minus theta y1 plus theta y2. Okay, and now here comes a little bit of algebra. Let me first write down the formula, and then I will quickly tell you why that is an equality. So y1 minus beta x plus theta y2 plus alpha x. And I claim this is an equality. Why is this? Well, if you look here inside, into this argument here, then what is this? Maybe in yellow. This is equal to 1 minus theta y1 plus theta y2, and then what's the rest? Well, the rest is x times theta alpha minus beta 1 minus theta. Okay, so there's a bracket with a factor x in front, and inside the bracket you have theta alpha minus beta 1 minus theta. Yeah, but this bracket here is identically 0 by this definition. You can check. Just substitute or plug in theta. You will see that this second bracket is equal to 0, and that's why you have the equality up there. All right, good. And now you apply convexity of p, right? So this is 1 minus theta something here. And remember, p is a function that is convex on the whole space x, right? Not just on the subspace, because here this quantity here, of course, in general is not in y anymore, right? Because x is an element which is in the complement of y, and likewise here. Nevertheless, these are elements in x because we're playing around with vector spaces. Okay, so you can then use the fact that p is convex on the whole space. You can pull out the 1 minus theta, and then you get p y1 minus beta x plus theta p y2 plus alpha x. Okay, that's what you have on the right. And then now use linearity of f. F is a linear functional on y, and here everything is nice because this is an element in y, and this is an element in y, and since y is a subspace, that convex combination 1 minus theta y1 plus theta y2 is in y. So indeed I have on the left 1 minus theta f y1 plus theta f y2, and then I'll just sort of copy what I just figured out, because this here, what I just wrote down, this here is just the left, is equal to what's here on the left. So it is therefore bounded by 1 minus theta p y1 minus beta x plus theta p y2 plus alpha x. Okay, so we have this, and now we are done, because now multiply through by alpha plus beta, which is a positive number, right? So remember, theta was alpha, or was it beta? Yeah, it was beta divided by alpha plus beta, beta plus alpha plus beta divided by alpha plus beta. So now if you multiply this equation here through by alpha plus beta, you kill the denominator, and then what comes out is, which yields, well, you have beta here, p y2 plus alpha x plus, now this one here will give you an alpha, p y2 minus beta x. This is at least, no, yeah, okay, and then the same prefactors, 1 minus theta and theta, so alpha f y1 plus beta f y2. Okay, that's what you get here. Yeah, and this is precisely the stated inequality after rearrangement. Okay, you bring the terms with alpha to one side, the terms with beta to the other, and then you divide by alpha times beta, and then you have the inequality. Okay, this yields the desired inequality after rearrangement. Okay, that's that. Okay, good. Nice. Now, why do we care for it? Well, because of the following proposition. And this will explain what I meant earlier. So we will try to extend that subspace Y one vector at a time. And then once we have convinced ourselves that we can do it once, then we will use Zorn's lemma and jump, to the general case. So given x, y, f, p as in the assumptions of the real Hahn-Banach theorem, so x real vector space, y subspace, f a linear functional on y, p a convex function on x. Okay, these are the assumptions, and now again we take a vector in the complement of y, again assuming here implicitly that y is not already all of x. I mean, if it is, then the statement of the Hahn-Banach theorem is trivially satisfied. Just take capital F equal to small f. Okay. All right, so an x in there. There exists a linear functional notation will be f with a circle that is defined on y circle, which is sort of one vector bigger than y is. So y circle is the sum of these two subspaces. So the first one is just y, and the second one is the span of that one element x. So in other words, all scalar multiples, real scalar multiples of x. Okay, and this is the sum of two vector spaces here, this plus. All right. So now the claim is there exists a linear functional defined on this, well, one element bigger space, y circle, so that it has the properties that we want. That is to say, it is still dominated by the convex function for all z on the bigger space, y0, and if you evaluate f0 on a vector that is back in y, then you're back to the small f. Okay, that's the crucial part in the proof. Once we have established this, once we understand how this works, then Zorn's lemma will do the rest, albeit in a non-constructive fashion. Okay, proof. Given that every z in y0 is of the form z is y plus alpha x for some unique y in y and alpha in R. So the question is, why is that true? Well, it's like in the projection lemma, that argument. So in the projection lemma in Hilbert spaces, it was that you have a closed subspace, and then you can write any vector in the bigger space as a sum of something in the closed subspace and something in the orthogonal complement of the closed subspace, and that representation is unique. And this is kind of the similar thing here. So how to prove that you can do this uniquely? Well, as usual, if you can find y1 and alpha 1 such that you have this equality, and likewise y2 plus alpha 2, and then you play around a little bit here with the inequality. So y1 minus y2 is then, let's think here, alpha 2 minus alpha 1x. Okay, so now notice here, so y is a subspace. That means that difference here on the left, y1 minus y2, is in the subspace. Yeah, but apparently this difference is equal to the right hand side, so that means that the right hand side is in y. Yeah, but now if that difference of the alphas, alpha 2 minus alpha 1, were not equal to 0, then of course you could just divide it out because it's a scalar. And then you would find out that x is in y. Yeah, but that's a contradiction because x is in the complement, right? Hence, that difference has to be equal to 0. That will give you that alpha 2 is equal to alpha 1. And once alpha 2 is equal to alpha 1, then this equality here says that the left-hand side has to be 0. So y1 is equal to y2. Okay. So indeed, that representation is unique. Good. Now having it, we now define, given that every y is of the form for some unique y, we will define the linear, okay, let me erase here these things, the linear extension f circle y circle to r s. Okay, there's a natural way now how to do this. So that z element here is y plus alpha x, so I will just define it as f of y plus alpha f0 of x. Okay, and at the moment, this guy here, the first one, is known because f is given in the statement of the theorem and this proposition. This here is yet unknown, so this I still have to define, but that's at least the idea what I'm gonna do, right? So, and thus need to make sense of f0x 4x in, well, the complement of y. Why do you want it in this form? So remember, one of the properties that we want up there is that that extension reproduces the small f once you restrict your attention to the subspace, and that's precisely what this formula achieves, right? Because if that element z here is in y, remember that representation up here is unique, then this will only happen when alpha is equal to 0, right? Yeah, but if alpha is equal to 0, of course, this guy here is gone, and then you indeed reproduce the small f. That's why this is a good candidate. So now what we have to do is we have to choose that second term here, f0 of x, in such a way that the inequality here holds true, and then we are done, right? Because, I mean, the fact that this is linear, that's clear, because the map f is a linear functional, so that piece there out front is linear. And if you have two vectors, z, well, then they will differ the sum of two. Let's write it here. It will be of this form here, right? So you have y1 plus y2 plus alpha 1 plus alpha 2x. So the y part is okay because small f is linear, and that alpha part here out front, of course, is trivially linear. If you have there, instead of alpha, alpha 1 plus alpha 2, you just split them up, right? You don't have to do any splitting here in the f0 part, okay? All right, good. So now how do we make sense of that remaining piece there? Well, that's precisely where we need that inequality that we just prepared, okay? So with star in place, the desired inequality f0z at most pz on y0 is equivalent to, and that you should check for yourself. So if you stick that inequality in there and z you represent as y plus alpha x, then this is all equivalent to, well, essentially two inequalities. So fy1 plus alpha f0x less than or equal p y1 plus alpha x. I will tell you y2 inequalities. fy2 minus beta f0x less than or equal py2 minus beta x, and this is for all y1, y2 in x. x and alpha beta positive. Why two inequalities here instead of one? Well, the thing is, you need to satisfy this guy here when you represent z as y plus alpha x for all real alphas. Okay, so, and whereas here this double inequality, in one of them the parameter is positive and the other one is positive as well, right? So you derive one inequality for positive real parameters and the other one for negative real parameters, and the negative ones you just write as minus something positive. That's why you have two. Okay, good. All right, so but now this is of course equivalent because it contains the quantity f0x on both sides. So this is equivalent to, now you just do the algebra, that is easy. So 1 over beta fy2 minus py2 minus beta x, f0 of x in between 1 over alpha. And that's precisely the way the inequalities were written in the proposition right before this one. So you have this, so in turn any value for f0x with, so let's make it a bit tight here, so supremum beta positive y2 in y with 1 over beta fy2 minus py2 minus beta x, and f0 at least of this magnitude, and then at most the infimum alpha positive y1 in y 1 over alpha py1 plus alpha x minus fy1. Okay, so in a sense I want to achieve this double inequality up here, and in such a way I have to choose my f0 of x. Okay, and of course I want this choice to be independent of the y's, the betas and the alphas. So what I do is I optimize both sides. I take the upper limit from the left, that would be the supremum over the beta and the y2, and I take the lower limit of the right, that would be the infimum over the alpha and the y1. And notice these extreme values, they exist. This is a consequence of the proposition, because that left hand side is bounded by something with y1 plus alpha x, right? So these exists. Okay, so with this choice, for f0x we satisfy the desired inequality and the proof is completed, right? Remember earlier I said that all the other things are already in place and the proof is completed. Okay, so that is the preparation for the proof of the Hahn-Banach theorem. Now we will use Zorn's lemma early on in the next video to complete the proof. Okay, I'll see you then.